Hello students, welcome back. Very happy to see you. So, let us start with the next module of the chapter, rotational motion. What's the module? Yes, see over there. Rolling motion without slipping. Now students, this is a very interesting module. Now what we are going to do in this module is, we are going to derive an expression for linear velocity of an object that is rolling down an inclined plane without slipping. Is that clear? So, are you geared up? Fine. Let's move on to this module. Now students, for this module, again, let me consider the inclined plane and a solid sphere kept at the top of the inclined plane. Let M be the mass of the solid sphere and R is the radius of the solid sphere. Now this solid sphere is at point A, which is at the top of the inclined plane. Now students, inclined plane. So let h be the height of the inclined plane, and one important thing, theta. What is this theta? Yes, very good. This theta is called as angle of inclination of the inclined plane. Now students, is this sphere, is it moving or is it at rest? Of course, it is at rest. So then we can say the initial velocity of this sphere is 0. Now students, when I release this sphere, what will happen? Oh yes, very good. This sphere will roll down the inclined plane. Now, this sphere is not just rolling, it is going to roll without slipping. Without slipping means this solid sphere will perform a pure rolling motion. So remember this, without slipping means it is a perfect, pure rolling motion. So this solid sphere has rolled from point A, which is at the top of the inclined plane, to point B, which is at the bottom of the inclined plane without slipping, pure rolling motion. So, during the rolling motion, the solid sphere has attained a linear velocity v. So what we need to do? We need to calculate an expression. We need to derive an expression for linear velocity. Is that clear? Fine. Now students, all of you know law of conservation of energy. What is law of conservation of energy? Yes. Now you will answer. Law of conservation of energy states that the total energy of a system is conserved. So then we can say, according to law of conservation of energy, the total energy of this solid sphere is conserved. Now, what do you mean by this? Initially, this solid sphere, where it was at point A. Was it at rest? Yes, it was at rest. If it is at rest, what energy will it have? What energy? Yes, it will have potential energy. Now, when I released it, what happened? The solid sphere rolled down, rolling motion, it was moving. So when it is moving, what energy will it have? Very good, it will have kinetic energy. Here it is rolling kinetic energy. So, as per law of conservation of energy, I can say that whatever potential energy this sphere had at point A got converted to rolling kinetic energy during the pure rolling motion. Is that clear? Because energy can either be created, not destroyed, it can be transformed from one form to another. So here we can say the gain, alright, here the sphere is gaining some kinetic energy, rolling kinetic energy. So the gain in rolling kinetic energy is equal to the loss in potential energy. So at A, potential energy, it loses it, and that is converted to rolling kinetic energy. Is that clear? So gain in rolling kinetic energy is loss in potential energy. How? As per law of conservation of energy. Fine. We all know what is rolling motion. What is rolling motion? Yes, very good. Rolling motion is a combination of translational and rotational. So rolling kinetic energy will be kinetic energy of translation plus kinetic energy of rotation, which is equal to potential energy when the sphere was at the top of the inclined plane. Fine students, let us carry this forward. After this, it's formula time. Kinetic energy of translation, what's the formula? Very good. Kinetic energy of translation is half mv square. Kinetic energy of rotation, yes, previous module we have discussed, come on. Kinetic energy of rotation, what is it? Yes, very good. Kinetic energy of rotation is half I omega square, I heard you, is equal to potential energy. Come on, you know the formula for potential energy. What is it? Yes, it is mgh. Now students, we can just simplify this expression. How to simplify this? We can write this as half mv square plus, hold on, moment of inertia, formula. Yes. I know that. You are saying, sir, many formulas are there. Which formula you want? Moment of inertia and radius of gyration relation. Which formula? Any guess? Very good. We have here I is equal to mk square, mass into radius of gyration square. So then half I omega square can be written as half mk square omega square equals to your mgh. Now students, further you can simplify this. How? Half mv square plus, hold on, omega We all know the relation between linear velocity and angular velocity. What is omega? There you go. Omega is V by R. So we can substitute omega V by R over there. Omega square. So it will be V square upon R square. So you will get half mk square V square upon R square equals to your mgh. Now students, what can we do? See there? Any term common? Oh yes. I see half mv square is common. So can I pull out half mv square? Yes. I can put half mv square common. What I will get inside the bracket? I will get 1 plus k square by r square equals to mgh. Now, any term can be cancelled. Yes, you see that mass can be cancelled. Then what you will get? You will get half v square into 1 plus k square by r square equals to gh. Now students, we are coming very very close to the expression. What we need to find out? We need to find out v, linear velocity. Yes or no? So, we can get v square first. What is v square? Come on. V square will be 2 into gh upon 1 plus k square by r square. This is your v square. You have v square now. Can you find out v? Oh yes. V will be nothing but, it will be root of 2gh upon 1 plus k square by r square. So, this is the expression for linear velocity of the solid sphere rolling down the inclined plane without slipping. Is that clear, students? Very simple. I used law of conservation of energy. I got this main formula. Loss in gravitational potential energy is equal to gain in rolling kinetic energy. Then I substituted all the formulas and I got the expression for linear velocity. Is that clear? Very simple, students. I'm very sure you can do it. Until then, I'll meet you in the next module. Till that, keep working. You can do it. Rise and shine.